Good evening. We are team number 5. I'd like to take this opportunity to introduce our team members, who are Mrs. Katina Blue, Miss Yolonda Burgess, Mr. Robert Hankins, and yours truly, Mrs. Terri Pullen. Again, we are team number 5. This team has been assigned to determine a computer programming language that will be used to simulate and implement for our group project. Our team has also been assigned to write the programming code to execute the program. The programming language that the group chose is Python. Python is a code that generates a very large prime number, whereas another creates the user's public and private keys, and a final version will encrypt and decrypt the code. Python is an interpreted, high-level, general-purpose programming language. And someone may be asking, what is a high-level programming language? Well, it is a programming language with strong abstraction from the details of the computer. In contrast to the low-level programming languages, it may use natural language elements, be easier to use, or may automate, even hide entirely significant areas of computing systems, making the process of development or computer programming much more simpler and understandable. This is in contrast, of course, to the lower-level programming language. And so this is primarily the reason why we chose Python, in addition to it being an open source code and pretty standard on the market today. And so I'll go ahead and pass on to the next presenter to talk about cryptography. Thank you.
What is cryptography? Cryptography is the art of writing or solving codes that allow information to be kept secret. It is a method of protecting information and communications through the use of codes so that only those for whom the information is intended can read and process it. The prefix crypt means hidden or vault, and the suffix graphy stands for writing. Earlier, cryptography was effectively synonymous with encryption, but nowadays, cryptography is mainly based on mathematical theory and computer science practice. Cryptography converts data into a format that is unreadable for an unauthorized user, allowing it to be transmitted without unauthorized entities decoding it back into a readable format, thus compromising the data. Information security uses cryptography on several levels. The information cannot be read without a key to decrypt it. The information maintains its integrity during transit and while being stored. Cryptography also aids in non-repudiation. This means that the sender and the delivery of a message can be verified. Lastly, cryptography also allows senders and receivers to authenticate each other through the use of key pairs.
The relationship of public and private key with cryptography in the RSA algorithm. The public and private keys are used together in cryptography. The public and private keys are a pair of keys selected so that one is used for encryption and the other used for decryption. The private key used in this algorithm is like the secret key used in symmetric encryption. The private key is kept secret. This type of cryptography is known as public key cryptography. Public key cryptography is also known as asymmetric cryptography. This type of crypto system is different from its predecessors because its algorithm uses mathematical functions rather than substitution or permutation. Public key cryptography works by converting characters to numbers and then performing math on those numbers. Public key is special because it converts multiple characters into an integer called a block, and then encrypts one block at a time. The key used for encryption or decryption depends on the type of algorithm chosen. Once the keys are defined for encryption or decryption, the sender and receiver must each have one of the matched pair of keys, but not the same one. For security purposes of public key encryption, the following must apply. The first thing must be that one of the keys must be kept secret. The second thing, it must be impossible to decipher a message if one key is kept secret. And thirdly, knowledge of the algorithm plus one of the keys and samples of cipher text must be insufficient to determine the other key. Public key crypto systems can be classified according to its application into three broad categories. Those categories are encryption, decryption, digital signature, and key exchange. For the encryption-decryption category, the sender encrypts a message with the recipient's public key, and the recipient decrypts the message with the recipient's private key. For digital signature, the sender signs a message with its private key. Signing is achieved by a cryptographic algorithm applied to the message or to a small block of data that is a function of the message. And the last category, key exchange. In key exchange, two sides cooperate to exchange a session key, which is a secret key for symmetric encryption generated for use for a particular transaction or a session, and only valid for a short period of time. Some algorithms can be classified as all three of the categories. The RSA algorithm is an asymmetric cipher that can rely on all three applications. This means that it works with two different keys. In other words, it has to use a public key and a private key as shown in our project. In RSA, the decryption will never use a public key. Therefore, the public key is for encryption and the private key is for decryption.
Thank you, Katina. And also, well said to the rest of the group. That was a good high-level overview of how RSA, cryptography, public and private keys all relate and allow a user to transmit data to another user with the confidence that their message will be kept secret. Up next, I'm going to be showing a live demonstration of how everything that was just explained works. To do this, I'm going to use a simple code that has been referenced online. You'll be seeing a few different Python codes live in action, and I'll be explaining the details and outcome of each and how they play into RSA cryptography. First, we have a prime number generator. Prime numbers are extremely important for private and public keys. Actually, large prime numbers are what make RSA so powerful. It is very difficult for hackers to determine the factors of huge prime numbers that make up our public and private keys. So with that, it is also very difficult for humans to generate true prime numbers that are this size in an efficient manner. For this, programming languages like Python are used to generate these numbers in the background, while the user usually never notices it happening. Let's take a look at how this is done. So first, we open the Python app. Using this code right here, this is our prime number generator code. We can import that program. Now that it's imported, we can type in a command prompt to be executed. And if we type in the right thing, we'll see exactly what happened. It's taking its time, but as you can see, using that Python program, we were able to generate what you see here is a very, very, very large prime number. Now, this isn't a primary code that was used in this course, but we just included this more so for supplemental value and to demonstrate how codes are used to generate these large prime numbers and just how big they are, and how you can see it would be very difficult for a human to do this in an efficient manner, you know, for all the different data transmissions that take on day to day in human to human interactions, computer to computer interactions, whatever the case may be. Up next, I'm going to demonstrate what it looks like when a user has a public and private key created for them so they can securely transmit data. For this, we'll be relying on another code, and I'll show you the code for that. It's titled Make Public Private Keys. The version is Rob's version. And as you see, we have our code. It's importing some other codes that were already created. This right here will create our public and private key pair. And then we've got the formula that's often mentioned in our textbook, the mod inverse formula. We're defining our public and private keys, and some more details for how this program works. Let's take a look at it in action. First, I want to show you this folder right here. It's my Python folder where I keep, you know, all the programs that are running, because when they're executed, they will usually store files that come from those programs in the folder where that program originated from. So if we look here, you see this folder is called Python. You don't see anything that says public or private key. For this, we're going to rely on our command prompt, which I already have opened. I've already opened this, and if you want to look at the history, the first thing I did was run the command prompt. I changed the directory to my documents directory. I pulled that directory open to see what files were in there. Again, I changed that directory to Python, where these codes in the background are stored at, so that when I type in my next command prompt, I can easily get to those codes. So we type in Python, we find the name of the code we want to make, which for this one, it's going to be make public private keys Rob. So we type that in. .py, and then let's sit back and see what happens. Oops, I just realized I left the C out of public. Let me do that one more time. My apologies, but shouldn't be much of a delay. Now you see that the program is executed. The first thing it says is it's making key files. It's generating P and Q primes, which means it's generating our public and private keys. P, public, Q is for our private. It's relatively prime. Using that D mod inverse formula, we've got our huge public key. So when someone wants to send me a message, they'll be able to find my public key. They'll send a message using that public key, and only I, having this private key, will be able to decrypt that message. If someone were to intercept this message and try and hack it, the only way they'd be able to do so is by being able to produce this large private key from the known public key information. And you see there's some more information down here on the public key. It says it is a 617 and 309 digit number, and it's writing the public key file to my documents. And the same with the private key. So we come back over here, and now remember, as I mentioned, these were not here before. Let's open one up. You'll see this is our private key, now stored in this folder. And the same thing with our public key. At this point, now that we've generated our public and private keys, we're ready to encrypt and decrypt a message. As Katina mentioned earlier, this is typically done in RSA by converting string characters into integers and then placing multiple integers into a single block. This is another key component of RSA technology. I won't go into all the details on that, but I did want to highlight it and let it be known that this is a very important step. So the final step of RSA, our RXA demonstration is to convert a plain text string character message into an encrypted message that no one can break down unless they have the private key. And for that, we're going to rely on this code. This code and this code right here are the same. The only difference is the mode is different. In this one, it's encrypt. So if we want to encrypt the message, we rely on that one. And in this one, it's decrypt. But for our encrypted message, let's change this to something like, we tried very hard on this project. It was tough, but we believe we succeeded. Type that in, save that. Now, we've got our message saved in our program, and this is what happens in the background whenever you send someone an email, something like that. This is happening in the background. So again, let's close out of some of these. Let's go back to our command prompt. Let me open the directory one more time so I can see the files. We're going to run the Python program public key cipher rob encrypt.py. Execute that. Got to go back and make one more change. The character, for this simple example, we didn't include all characters, so a comma, unfortunately, is not included. But that's actually a real easy fix for this. Of course, in the real world, something like a comma would be included, but just to illustrate a very simple example, we did not include those, or excuse me, the Python code we referenced did not include those because it was meant to be simple just to help the user understand. So come back here, execute that same code. Now that let's see, save that. Huh. I'm going to pause the recording for a second just to figure out what's going on. Okay, sorry about that. I didn't realize I had 2 commas in that one sentence, which is why we got the same error message. Now that those are both deleted, let me save that, make sure the most recent file saved, execute that code, and boom, there it goes. It explains to you what it's doing. It's encrypting and writing to encrypted file text. Here's our encrypted text. So that message that we just typed out, saying that this project was tough, we tried very hard, we believe we succeeded, looks like this. So if someone wanted to try and intercept this, this is all they would receive. This random number blocks right here is all that they would receive. And they wouldn't know what to do with this unless they had, theoretically, unless they had the private key. Now, someone with the private key, let's move over to a different code. We'll move over to our decrypt code. This decrypt code has the private key, or at least a code for the computer that it's executed on to search for the private key so that it can decrypt that message. So nothing that needs to be done here. I'll just save it just to be sure. But if we come and we run the same code, and I change this to decrypt, we should be able to, let me just make sure. Should be able to run this code. You see what it's doing? It's reading from encrypted file text and decrypting. And here we got it, decrypted text. We tried very hard on this project. It was tough, but we believe we succeeded. Of course, there are no commas in there. Those were not characters that were included. Commas removed. You see we have our sentence. And that right there is a very, very simple, high-level demonstration of how a plain text message is converted to an encrypted block of integers and then back to a readable plain text message. By working through this project, researching, relying on our references, and just coming up with as much information as we can, the entire group walked away with a much better understanding of exactly how RSA cryptography works. The one thing I will say is, the codes we reference, they are by no means meant to be used, officially. You will want much more complicated code, just so there are really no chance of a hacker being able to intercept your message. We hope you appreciated our demonstration. And up next, We'll just be going over a couple final items, what the team learned, what we took away, what was most difficult, and then we'll be closing out. Thank you. Going through this project, the group definitely had its highs and lows, things that, came easy and we had some familiarity with, and things that were a little more difficult. The most difficult thing for the group was really the complexity of programming languages. When we did the survey, some of us mentioned that we had, minimal experience with these programming languages, but as we talked, we realized no one really knew much about how to write and execute a programming language. So this was a huge learning curve. We definitely had to research and rely on programming codes that were already built, seeing as none of us had the expertise to build one ourselves. And we didn't have the time to learn that. We weren't taught that throughout this course, and that's not our expertise. We didn't want to rely on anybody else because this is our group project. Outside of, resources that are free to reference online, we wanted to make sure this was done in-house. And so that's where, the most difficult part of the project came into play. However, with that being said, that was also the most interesting, or not interesting, but the most fun part of the project. Once you do begin to understand a little bit how a Python program works, and then you get to see it executed, and then you get to see the outcome of that execution, just like we demonstrated, it makes you feel good. It makes you feel much better and comfortable with understanding just a little bit on how computers work and how impressive computers can be with being able to easily just, computate huge numbers or give you this crazy outcome that a human could never do in that amount of time. That's the exciting stuff. As far as the most interesting thing the group walked away with, we'd have to say it was just how large the prime numbers can get. As funny as that sounds, we had no idea that the prime numbers, which are very important for, RSA cryptography, got to be the size that they did. These numbers are insanely huge. And then there's even more, on a deeper RSA or more intricate, they take prime numbers and multiply them by each other and then use that as a key. And that's even, more difficult to break down and hack. And, we demonstrated that in our example, and you saw just how large the numbers got. So those were Team 5's key takeaways from this project and in this semester, I would say, as a group. So with that, it does conclude our presentation. There is one more slide after this. That's our references slide, where we cited all the resources we relied on. And so we want to say thank you. We appreciate, having you as a professor this semester. We definitely walked away with some key learnings, and we appreciate, the opportunity to dive deep into how RSA cryptography works. So thank you and enjoy the rest of your summer.